Hi everyone and welcome to DVCon Europe 2021. This is the second panel session today. So I am Tran Nguyen, I am the panel chair of the panel. The panel today is about can ML be the driver of next generation verifications? So we have a lot of fantastic people to discuss around the panel. It will be moderated by Carl from Cambrian AI Research. And this is topics that I know that everyone is talking about, and we will be excited to hear how our panelists will discuss about this today. So this panel is pre-recorded. This will play live during the panel sessions, and there will be some panelists online, and they can answer your question if you have to put them on the chat. Or alternatively, we can take your questions and answer them offline later on. So let's start. I'm happy to welcome Carl, our moderator. Carl Freund is the founder and principal analyst from Cambrian AI Research. Carl is founder and principal analyst of Cambrian AI Research. He explores AI and HPC hardware and cloud services providers and lives near Boulder, Colorado. His clients include dozens of public and private semiconductor companies for whom he publishes research papers and provides marketing advice. So I let you now, Carl, to start introducing our panelists.
All right, thanks, Tran. It's been a real pleasure to be here. I've been interested in how semiconductor designers are using AI, and I've explored using AI for design optimization, physical design optimization especially. And the area of design verification use of ML is new to me. So I'm looking forward to learning more about this from this robust panel. So we've got Tushit Jain, a senior director of machine learning and research at Qualcomm. John Rose, product engineering group director at Cadence. Raviv Gal, manager hybrid quality cloud technologies at IBM Research. Daniel Hansen, founder and CEO of Verifider. Adnan Hamid, CEO and CTO of Brecker Verification Systems. And Darren is a principal design verification engineer at Renesas. So with that, why don't we turn it over and we'll start a discussion. What we're going to do here, we've asked each panelist the same question, two questions actually. One, what are the key problems that you're trying to solve using machine learning or AI? And second, how do you get the data? What is your source of data that would help you formulate the models that can allow you to optimize design verification? So I think we're starting with Tushit, is that right? There we go. I'll turn it over to you, Tushit.
Hey, thanks, Carl. I'm excited to be here on this panel and learning from everyone here. What we're seeing at Qualcomm, and which is an important problem at our scale in Qualcomm, is essentially driving coverage closure and finding ways to speed up coverage closure using ML. We're also presenting a paper at DVCon this time on coverage closure. And one of the interesting aspects of this paper is that we're using the fact that most circuits can be represented by graphs. And so we're seeing that there's a lot of application of graph neural networks in VLSI design, because as you know, most circuits, analog or digital, can be represented as graphs. So it's a very interesting data structure to work with. Unlike computer vision, where you work with pixels, in VLSI graphs are natural. And some of the other use cases we're seeing in this area is kind of speeding up debugging of simulations. How do we automate root causing of problems that people are seeing when a simulation fails? The other case that's really exciting for people is to see if they can recreate bugs that are being seen in emulation or post-silicon. Can they somehow recreate them in design verification because there was a slip in design verification? And another very interesting, very challenging problem that people come up with is the problem that, very often when they go through design verification, they're realizing that there are missing coverage models, missing assertions that they should have checked for, and they're looking for ways by which machine learning or AI can help address that. We're also seeing, I would say, application of all sorts of techniques of machine learning, supervised learning, unsupervised learning, reinforcement learning, and all these problems. We're seeing data sources of all sorts, where you can easily think of the waveforms that come out of simulations as a data source. The coverage databases are a very rich form of data, as well as text simulation logs or test plans that people have. So as you can see, using all these different data sources, you can even pose some of these problems as language learning problems or graph problems. So I hope that gives you a sense of the kind of problems we're solving at Qualcomm with machine learning and DV.
Sounds good. Sounds exciting. Next up, I believe, is John Rose.
Okay, hello.
Yeah, so out that John and I are actually almost neighbors. He lives just about 15 miles north of me here in Colorado. So.
Yes, very close. So to go along with what was just said, I think our conceptions of the problems that we need to solve are pretty similar. So what we're looking at, so there's a lot of data that we get in verification, and as mentioned, we get all of this coverage data and all those waveforms. We have log files, we have data from randomization, we have the design itself, the specs that we get, the performance specs or power intent or whatever. So we have all of these various data sources. And, the question is, okay, well, so what do we do with all this? We've got this data from everywhere. What can we do to help either the engineer be more efficient or the machines be more efficient? Like we have these two kind of competing areas. So one of the objectives, or a few of the objectives that we work on, one is just resource maximization, right? So how do we make our simulator more efficient? How do we make the layout tools more efficient? That's just kind of like taking your heuristics that you did without machine learning and making them better, because now you have all of this data that you can use, you have at your disposal. The more interesting, I guess, point would be, how do we help the engineer be more efficient, right? So this would kind of come in the form of, say, failure triage. We've got all of these failure signatures, these ways that we see problems, but can we help the engineer categorize these failures and then root cause them more efficiently, right? That's the kind of area that machine learning has a lot of applicability, because there's no, I guess, necessarily wrong answer. It's not like you're going to lose something if ML takes you down maybe a wrong route. It may not be as efficient, but it has the possibility of helping you in a significant way. This is true also with like bug hunting types of things. The machine learning has the ability to, you as the user, if you can help direct the tool and say, okay, I'm seeing that I'm not, let me rephrase, I'm getting bugs in this area of the design, and I don't seem to have enough representation in my regression environment to hitting that area. Can the machine learning help me generate more runs and provide more simulation that has an opportunity to stress these corner case areas that may expose new failure signatures? And then, of course, what was mentioned, the coverage closure. So there's a number of things that AI and machine learning can do in the closure space, where you have holes in your coverage, and if you can again, have the machine learning tool focus on areas around the holes. If you, as a user, for example, can provide information, or if the tool can figure out automatically prerequisites to hitting these holes, then it's possible to generate runs that will help you hit those holes more quickly. And then in the straight resource maximization space, you can remove a lot of redundancy with the machine learning, because it can analyze what you've done. In the case of, say, verification, you've run, say, 10,000 runs nightly, but if only 2,000 of them are doing anything interesting, then you're potentially wasting a lot of resources, where if you can use those resources to focus runs at corner case areas or something along these lines, then you have a better chance of exposing problems you hadn't seen before. So that's kind of the general areas that we're looking at. But I mean, there's so many possibilities. It's almost an endless array of things that machine learning could provide some value. And I think the key for us and everyone else is just figuring out where can these techniques be applied that will really help engineers do their job better without concern that they're losing some control over what's happening and may, in the worst case, miss something that should be caught. So I think that's it for me.
Interesting. Thanks a lot. Thanks a lot, John. Next up, we've got Raviv Gal. I know during our first meeting, Raviv was not shy about expressing some doubts and skepticism, but I'll turn it over to him, and let's hear what you got to say, Raviv.
Okay, thanks, Carl. So we have been working on using machine learning AI for verification for more than 5 years now. And what I've seen was not a revolution. It's more of an evolution. And this is not bad, but it's not like the revolution that ML did in other areas, like computer vision, or distinguishing between cats and dogs, and some more practical things other than this. So why is AI ML for verification hard? So maybe it's not that hard, and we are missing something, but let's go with this line. So first, verification, and this is also for the entire area of EDA, is a mature area. Sophisticated, complex chips were manufactured before ML was a big hype. We have mature tools, mature methodologies. This is hard to beat. We are lacking labeled data. We have a lot of data, not all of it, or most of it is unlabeled for our needs. I can elaborate it later. There are no public open benchmark that we can measure our progress like we have in the formal verification community. The data availability, the option for big company to open their data for academic collaboration is problematic, which limits the ability to collaborate with academia. The data is changing during the verification process, right? So can we learn from what we see, what we simulate in the beginning of the process, when we are in the middle of the verification, or at the end of the verification? And last, AI or machine learning is about generalization. What we try to do, in a sense, in verification is to break this generalization. We don't want to run again and again the same test, right? We want to do new things, find new bugs. So how can we learn from what we already did to the new things that we are trying to do? And my belief is that there is no other way than the hybrid approach. So there will not be, I'm not aware of anything that will throw away all the knowledge that we have in this area and come up with a new solution that will ignore it. So what we need to find a way to do is to combine the current state-of-the-art technology, domain knowledge, expertise with AI and boost things. And a positive example that we have is regarding coverage closure, or the way we like to call it, coverage-directed generation, CDG. This was a very hot topic 20 years back. No real success in the industry. We came back to this problem 5 years ago with the hope that machine learning open new options for it. And what really helped us to actually break the wall was defining the problem as an optimization problem and use classic noisy function optimization problem, directive-free optimization. We use implicit filtering algorithm for it. This was published in a paper in this year date. Now, what we did with AI was boosting this iterative classic optimization algorithm with what we call lightly trained DNN. Now, think of it as we start using a DNN that is trained with 100 sample points, which is a ridiculous small number. And the DNN knows almost nothing, but along the process it learns, and it doesn't learn very well because we cannot expect the DNN to know about how to cover events in areas that we didn't provide data to train in. But however, we can show that this DNN acting as a weak learner can boost the classic optimization by a factor of 2. And these are 2 papers that we presented in MLCAD last year and this year, showing that this kind of using DNN to boost optimization problem can work with the implicit filtering algorithm that we use for the CDG, but also with other classic optimization problems. So thank you so far.
Interesting, Ravi. Thank you. Thank you very much. Next up, we have Daniel. Daniel, why don't you take us through your thoughts?
All right. So we are very much focused on automatic debug. We have a tool in this domain, and that's all we do. So all our ideas goes to one focused area. And I would say that our experience matches Raviv's very much in that I believe performance optimization problems is something you can solve with ML. So, but not everything. So in our case, we do automatic debug of regression failures, and that can take time because there are many potential sources for the problem, many different root causes. So the problem there is it can take a huge amount of time to go through all these potential reasons for test failing. And the solution we have done based on ML is to, at time 0, we do bug prediction, which is basically if you run regression testing and you have 100 new commits since yesterday, you do a risk analysis of those and give a number to each on how likely it is that that commit, which you have never tested, contains a bug or not. So that allows you to, instead of treating all 100 new commits as equals, you can just focus on the, say, top 5 high-risk commits, and then the problem becomes much smaller. And that allows you to go through this whole debugging process much faster. And the data we use is the revision control data, anything you can find in the repository, like Git, Subversion, Performance. We look at the code itself. We look at test results, historical, current. And from all that, we generate more than 100 features. And then those features we feed into this machine learning magic, and looking at historical commits, whether they were good or bad, we can then train the model to predict whether these future commits are good or bad. And that's part of our product already, and that works fine. But I would say that we have learned that you must have a framework to control whether the predictions are sane or not. You can't just have good predictions and expose the end user to that and expect them to be happy. You will just hammer them with the results of average quality. So, for example, it's okay to use ML to propose sentence completion in emails where user just click tab if they like the sentence and include it because it's so easy. But in our case, it's not okay to accuse an end user of having potentially created a bug and send the bug report to them and CC their managers, colleagues, friends, and mothers. This all needs to be checked. The whole tool needs to take it as a good proposal and needs to verify it to make sure it's true before it makes such an accusation. So taking this into account, I think problems can be solved with ML if either the prediction accuracy is very, very good, or more realistically, if you have a mechanism to filter out good and bad predictions with limited effort for the user. So if you want to really use ML, you should not think about the ML. You should think about this filter first, and then you can know. Okay, I can apply non-perfect but good on average results to the user, but filtered with this filter, and then you can attack domain after domain. But the trick is not to squeeze up ML prediction with some number. The trick is to contain it so you create a good use model for the user. All right. Carl, you're on mute.
Carl, you're still on mute.
Oh, it's like, where's the screen? I need an AI sometimes to find the screen I'm actually using. Okay, that sounds really good. Sounds like I see Raviv shaking his head vigorously, so it sounds like you guys have walked down the same path.
We're friends.
Yeah, absolutely. So let's hear from Adnan. Adnan, why don't you walk us through your experience in using ML for DV?
Thank you, Carl. So Brecka was arguably the hipster in verification and AI because we were doing it way before anybody thought it was cool. And in fact, when we started, we would never say AI because AI wasn't cool then. We actually came down not the path of machine learning, which is fancy statistics. We came down the path of planning algorithms or inferencing engines, which is fancy rule chaining, right? Just a different branch of AI. The problem we got interested in was what we see as a gross inefficiency in verification, right? That it's not just about optimizing coverage of what we have, but if we look at these projects, at each stage of a project, we're spending about 30% of our time, people, money on creating test cases, another 25% on debug, and most of that debug is debugging the test case, not debugging the design. So that's over 50% that you can save. And that problem repeats at the IP level, at the full chip level, and at the post-silicon level. So that's a lot of work that we can do better. So what my slides are trying to talk about are three things, right? How do we collect the input data for these inferencing engines or planning algorithms? How do we cover that? And how do we map it to all these platforms so you can define these tests once and use them everywhere? And really, this work was never so much about bringing AI into the picture. It just happened to be the right tool to solve the problem. The real question was, how do we define what our intent is, what our design is supposed to do? And the fact is, for every verification plan I've ever seen, if there are 10 items on the plan, I can pop out 50 more that needs testing, and the user will say, yeah, that's what I meant. And what happens is DV engineers, we pay them a lot because we expect them to infer those additional 50 on top of what we wrote. And then please go write all these test cases that cover them. And the real aha over here was, hey, not only do we need this information, so this is going to, I think what Raviv said, that right, we need the domain knowledge, but we need domain knowledge from many different domains. So how can we come up with a language that they all understand? And really, we went back to an idea that is, for our industry, ancient, right? Flowcharts or fault trees, right? NASA was using fault trees back in the 60s. You say, okay, here's how my rocket works. Here are the steps we go through at each step. Here are the decisions that I need to make, and here are all the things that can go wrong, right? So we have been quite successful in capturing whether you want to call it a fault tree or a flowchart, but getting people to describe their intention as a flowchart. Once we have that flowchart, really it becomes a matter of thinking about all the different paths through the flowchart. So that's how you think about coverage. And then we've got to think about how we reuse all these things, right? Because we don't want to have to write our USB tests, one for the block level, one for the full chip, one for silicon, which is what we do. Okay. So what does this all roll out to? Well, people have the designs. Our designs are complicated. Let's not try to minimize that. When you look at how engineers really think about coming up with their verification plans, they'll go to a conference room, get on a whiteboard, wildly draw all these circles and squares and arrows between them. They're drawing flow charts, explaining to each other what their intentions are. Unfortunately, that's the creative work. Then they'll spend the next 2 months trying to implement that work. What if we give them what I fondly call PowerPoint for DV engineers, right? Just give them a way to draw that flow chart into a tool in the way that you can generate code from it. And it turns out that everything we design is full of exceptions, right? There's this flow chart, but one of these flows don't work if you're in a particular mode because whatever. So we need a constraint flow chart. Again, not a new idea to us in verification. We're used to constrained numbers. This is just saying, hey, we have this flow chart, but with certain rules, certain paths are no good. And that actually has been quite successful, where people, once you get them into the mindset of capturing the intent of the flowchart as a hierarchy of flowcharts, they kind of get into it and they start discovering all kinds of things they don't know about the design, or they didn't know. So this is all just the construction is very valuable. And then after that, you have the flowchart. You flatten it into a big old graph. You send some inferencing engine after it, and it goes plans out your test cases. And now you have some strength, right? Because now you can say, hey, I'm going to risk optimize my coverage at each stage. What do I mean by that? Simulation is slow. I'm talking about system level simulation. So let's do onesies of each thing, right? As opposed to get guys into trying to cover every corner case of USB or something. Emulation is faster. So maybe I can do certain crosses, post it, and I can open up the doors. And then the last point that I have to make is this mapping and debug, right? So mapping is the point that whether you're UVM, full chip, or post-silicon, we always try to test the same basic ideas, right? We're just rewriting different tests for different platforms that do the same thing at different levels. Well, you send this planning algorithm off to just take your leaf operations and figure out how to apply it to each platform, and that works fairly well. And now you sent a planning algorithm to build a test. It started with some intent and worked out what steps were needed to test that intent. So it has a lot of high-level debug information to provide. And when something goes wrong, you can provide all the debug information to the user. So the combination of capturing flowcharts, planning algorithms to do the coverage, to generate the tests and do the coverage, and then finally map it to different platforms for the debug is what we've been doing. And so far, it has seemed to hold together quite well. Thank you.
Very nice, Adnan. Very nice. So obviously, you have to understand what the designers intended the function to be in order to properly test the outcomes. Yeah,
absolutely. So that's the work they got to put in, and it's really, today they're doing that work. Actually, they do 10 times more work than that, right? They're writing all those test cases by hand. So instead of writing 2,000 test cases, write one flowchart.
Interesting. Okay, thank you. Let's see, Darren, I think you're up next.
Yep, thank you very much. That was all very interesting stuff which went before. And like many others, the problem which I've seen is applied to mostly is how to close functional coverage more quickly with fewer simulations in random test benches, because we're all running thousands of simulations trying to close down that last amount of functional coverage. But there's one fundamental problem that I foresee or I see with this, and that's we're optimizing based on the weakest part of our environment and hence the most buggy code. So when we're running and debugging our test cases, we've got feedback in the form of code coverage to tell us how good the vectors are, or at least give an indication of it. We can use test bench code mutation to see how good our checking is and whether there are any holes in that. But when it comes down to the functional coverage, no one actually looks at it unless you can't hit it. You assume if it's 100% that it was all correct and you don't look at it again, and you only ever look at it if something's not as you expect and you don't know why you haven't hit it yet. But having said that, if you do apply ML, we found, well, we saw in the results on the project I was involved with, that you can improve the times to hitting your coverage significantly. But there's a drawback. If you're running fewer simulations, you get a loss of that serendipitous discovery, because I've yet to see a functional coverage model which really considers everything in your design. Engineers put a lot of effort into thinking of all of the possible combinations you can get in a design and trying to hit them. But when you're working in very large microprocessor type systems, it's the interaction between different parts of the system you haven't considered, which can quite often cause you bugs. The ML can also have problems if you're using reactive test benches, where you are seeing what's happening during the simulation from my initial vector set and then injecting or changing how the test works, because you can't easily foresee in advance what's going to happen from a given set of vectors in that case. So to try and mitigate this, people typically run more simulations or a little bit more soak testing to try and cover that serendipitous discovery. But then that leads to the question, how long is really long enough to balance that out? And in doing so, you're kind of negating some of the benefit that you were trying to get from ML in the first place. But maybe, is this actually the wrong problem? What I'm really trying to do is to find all of the bugs in my design, and coverage is simply a guide to get there and indicate the areas which have been more weakly tested. So, and this is kind of more of a wish list now rather than saying what we've actually used or could use, but we really want to use more data, because there's plenty of data around, but it's quite often coming from a disparate tool set. So obviously you can use code coverage and functional coverage. They will come from your simulation, but I've also got mutation coverage, which is saying, can I detect faults in my test bench? By my test bench, find the faults in the design. So is the checking good enough? As we saw in the Verifighter example, you can look at your code change records and then see what has changed. Is that an indication of what can go wrong? But it could be that the code I've committed isn't the one that's got the bug in it. It's causing a bug somewhere else in code that I committed some time ago. Code complexity is also of interest. The more complex the code, the more combinations of expressions, for example, the more likelihood there is there's something that's gone wrong. Cone of influence analysis, we all use formal in various parts, and that's got to do a whole tree of analysis which feeds into particular points. Could I possibly extract from that if I want to look at this endpoint, what's feeding in, and then analyze to see whether I could get a vector set to go in? I've got results coming from subsystem testings, SOCs, emulation results. I've got previous projects where I've got coverage data. Could I possibly reuse it all? So for it to be used more easily by the end user, the tools need to be able to share this data so you can analyze the complete set of what's available and get a better result. And ultimately, this means that the tools need to be more interoperable. No company really uses one vendor for everything. I mean, the tool sets I use come from several, and I've got other vendors knocking on my door saying, please use our new tool. If I want to do that and really gain from the ML, I need to be able to share the data from all of those tools and come up with a good prediction about how to actually solve my problem. Thank you.
Very interesting. Very interesting. Yeah, I'm sure all the EDA vendors would like to solve that just by saying, just only use my tools. That's just not practical. That's not the way the world works, right? Yep. All right. Well, this has been fascinating. I've got a couple of questions. I think it's time for the audience to start logging their questions, and we'll get to those either live or after the conference, in the case of where time zones made it impossible for people to attend live. I've got a couple of questions I thought I'd throw out there for the panel, and hopefully some of these will work for you. We've been talking about using ML and AI for DV. What about physical design? An area that I've done a little study in. Have your organizations been successful in using AI for physical design optimization for power, energy, or area optimizations? Anybody want to throw an answer at that?
Sure. I mean, I can kind of talk to some of the stuff that we've done. So we definitely see physical design as another interesting area to apply machine learning. We've used it in tape outs now. We're also working with universities, collaborating. It's also a little different from the DV challenges that you have. Very interestingly, in physical design, once the design has gone through synthesis or placement out, almost all IPs just look like are just a netlist, right? Whereas in DV, every IP is different. Like a bus is different from a CPU, is different from a memory controller. But I think physical design is a little easier than design verification because everything starts to look more homogeneous. But it's absolutely another key area to work in.
Yeah, that was my impression, is that in physical design, it's a little more straightforward. You're just doing a lot of basically game playing. I mean, you're just trying to play every possible move and see which one gives you the best results of meeting your objectives. Anybody else have any comments or experience you'd like to share?
Yeah, I can say two things. First, yes, there are such activities in my organization. I'm sometimes have the opportunity to review them or to share some ideas, but I'm lacking the expert knowledge or the domain knowledge that is needed to really do something meaningful in this area, I believe. Now, there is a workshop, the third one was just handled months ago, called ML-CAD. It is machine learning for CAD. I was honored to chair it this year. Most of it, as you can imagine, was not on verification, but was on the physical part. And I can say that my impression is that the observation that I shared at the beginning about no revolution, but evolution, there are success stories. I can quote a guy from Mentor Siemens, Jeff Dick, who said that in their ML boosted solution, about 1/3 of the algorithmic is machine learning and 2/3 is not. So gives some sense of where the PR and where the real value is. And there is real value, but I feel that sometimes we are misleading, I don't know why, ourselves, others, about how things can help and so on. Yeah.
Well, I think sometimes people want a simple answer when the answer cannot be simple, and using AI in physical design can give you options, but still takes a human, very talented, experienced human to figure out which one of these is actually the best to meet the needs of the business. What about failures? Anybody have are there some learnings you could share by some things that you've tried using ML for DV that really didn't pan out, that you could help our audience avoid making the same mistakes?
Well, we tried deep learning for our problem, which didn't work at all because it's just too little data. So it got the average value was the same roughly as ML, but with crazy variation. So our bug prediction tool then said sometimes every single commit is a bug, and then it said there's not any bug in sight ever. So on average, it was the same, but it was totally useless. And I think that's a sign just that there's too little data in our domain. And I think it's in the whole front-end verification, it tends to be too little data for anything but ML, really.
Mm-hmm. And that sounds reasonable to me. It takes a lot of data to train an accurate deep neural network. Other dead ends that people would like to share and help others avoid?
I'll offer one. So as we went down the journey of doing these planning algorithms for test generation, our first foray was to try to teach DV engineers, hey, think about the problem as a planning problem, because there's some strength to it. You get a much stronger view of what are all the things that can happen. And for many customers, this worked, including my friend Ravi, right, at IBM. But for many, it did not, right? It's teaching people a new way of thinking doesn't work so well. And that's what led to the evolution of, okay, just think of this as flow charts and have the tool deal with it. So I think one of the challenges that I'll throw out over here, right, is we can optimize the coverage and the tests we have. But Darren, it was you who said, right? Who says my coverage model is any good? Yeah. So I think a lot of this is about capturing the domain knowledge from the people, right? Because the fact is, if our objective is just coverage, write one line of RTL. I can cover it in one test. Does it do anything? Who asked for that? Nobody asked that. You just ask coverage.
I think I'll add a couple of tips, I would say, to people watching. I mean, one, I think Daniel made this point, and I'd kind of reiterate it, saying, when you're picking problems to solve, don't pick problems where you need 100% accuracy, because you want to pick problems where it's okay for the machine learning to give you something that is inaccurate once in a while. And you want to use that in a way that it assists designers. You don't want to try and replace designers, because very often the designer has a human intuition, right? And I think Darren brought that in, that you run tests not just because there's a functional coverage model, but the designer also knows that there was something that this test was doing that other tests don't kind of do. So your coverage models aren't always 100%. So always think of like machine learning as something that assists the human rather than replace it, because often the human intuition is doing something that isn't documented or is not written up, right? And the third thing I would say is that any machine learning problem that you start to work on, you need to think about how to represent the data mathematically. How does the data become a vector of numbers? And you should have some sort of an intuition of what the ML model is doing. You can't just, I mean, today I think a lot of people read popular media and they assume, you can throw a deep neural network at some data that is completely uncorrelated to the outcomes they want, and it'll magically get solved. I think unless you can you can think in your mind, what is this mathematical function or relationship the machine learning is trying to learn? I would say don't attempt to solve the problem just by throwing deep neural networks at it.
That sounds like sage advice to me.
On your point of it's okay to be right some of the time, right? Because this is necessarily true. Do you find that if we are trying to evolve technology, false failures are deadly to us, because once the engineers lose trust that our failures are real failures, they'll never look at another one again.
Right. Yes. No, I think
but just continuing from what you just pointed, one of the lessons we learned that, and it sounds trivial when I say it, when you have the machine learning output goes to an automatic process, it is more tolerant to accuracy, and then you can measure if this is good for your outcome, or we're looking at the overall process or not. When you use ML as an advisory system to expert, experts are problematic. First, because they are experts, and second, because they are people. And you fool them. What you need when you give such data as advisory, you need first to be accurate, but it's not enough. Tell me something I do not know, because if you always tell the trivial, they will also lose trust. Now I can share one of the things that we learn, and it is again trivial. Identify the right problem and have a clear understanding of how you want to use the outcome. One of our great failures so far was working on triage, trying to cluster problems, identify failures that represent new bugs, and so on. And we did a lot of mistakes over there. One of them was, looking at label data and, split it randomly. Okay, but this is a wrong approach, because what do you do in real life? You have the data of previous days to learn from, and you are looking at today's data. You cannot just randomize the data over time, right? The time series has meaning, okay? And another thing that we tried and failed dramatically was trying to use the simulation log without really breaking or understanding the structure of it. Because simulation log is not a book chapter. It is structured, but it's not clear because we don't have the structure in hand. So trying to use some NLP approaches, what we end up was that we were able to reverse engineer the test name from the simulation logs in a naive approach. So triage problem is still something that we hope to get back, but we could not beat a basic rule-based approach for it.
Interesting. Darren, you have your hand raised. You have something you'd like to share?
I was going to say, when just feeding back on something Ravi said, one of the problems we have if you're going to use simulation logs is we actually disable most of the messaging within the simulations to speed up the simulations to make them go through faster. So by definition, to get throughput, we're throwing away the information you then actually want to try and learn from, whether or not you understand the structure of it. The second thing I was going to say is that I think we need to embrace the fact that this isn't a black and white 100% or 0% result. And it's like weather forecasting. Yeah, there's a confidence level with it, and we need to be open with that. And there are tools out there which say, yes, I'll give you a statistical answer, and it's within 95% confidence that this is going to be correct. Yeah. Therefore, you're preparing people for the idea that, yes, sometimes I'm going to get something wrong. Yeah. I'm not trying to claim it's 100%, and it gets better acceptance. And as with all things statistics, it's easy to try and say it will happen or it won't, but in reality, there's always this margin of error, and we just need to make that clearer to people so that they're happy with it before we start.
Sounds like good advice. Set the right expectations. Yep. What is really possible here. So I think we're about out of time. I'm going to turn it back over to you, Tran, to kick off the question and answers. Thank you all very much, panel.
Thank you, everyone, for the
thanks.
Thanks.
Thank you.
So yeah, hi everyone. So there are there's some echo. So some echo in my mind. So there's some question on the chat, and I think that there's some discussion going on. So maybe Daniel or Ravi on the end, can you pop up and answer them live?
Hello. Hi, Ravi.
Hi, Daniel. Hi,
Hello.
Darren.
Hello, Darren.
I don't know, Ravi.
All right, so questions.
I think that there's some topic ongoing discussion from Mark that you guys reply or some comment globally. If you can, share it with the audience.
Yeah, maybe Mark or Raviv can start from where they've written the answers in text.
Okay, I can try. There is a comment from Mark about a good comment about, I think, that CDG, coverage directed generation, or these types of approach will not match the part in the verification process where new features and new tests are written. I can just agree. What I answered is that I think in all projects that I'm aware of, you never start from a clean paper. You always have your legacy test templates and verification environments, and you build your next generation upon them. So at your first step, you have things that you may want to optimize, and along the way you get more. So the claim, and if I was misunderstood here or someone else, that CDG-like tools will solve all the verification problems, no way. But this is the same things that you need to define coverage for these new features that you develop in your new generation. Still, this kind of technology holds a lot of promise for optimization, for improving both the quality and the efficiency of the verification process. I hope it answered the question, Mark.
Okay, if there's no other question coming in, I can just jump in and comment on an answer I did to submit. That it's very important to verify the ML implementation also, and especially if you go to a conference like DVCon, you must verify your stuff. Some tricks, some things are very domain specific, but some generic things you can verify, I listed in my answer there, such as when you extract features and you look at exactly the same window for live, during inference and training, you should get back exactly the same answer. So we have that as a test bench. We train, extract features, and then we run live and we extract features, and they should be the same thing. And not always is it possible to extract the features with exactly the same mechanism. There can be some differences because training typically maybe download data from stale data from a database that covers a large time period, whereas when you run live, it's a shorter time period. So there is a possibility for implementation errors. But so that diff is a good one. And other feature implementation checks you can do is to check that the ranges are good with assertions, check that there are different features don't conflict each other. If one feature says this is a big commit and another feature says this is a small commit, there's a bug somewhere. And above all, make sure that the features and the predictions map reality. If you're trying to predict what day of the week it is, and Monday comes in 80% of the cases, something is wrong because there are 7 weekdays. So with the ML, you can't know whether the exact same, whether each prediction is good, but you can see the distribution and compare it with the reality. So that check is also a good thing to do.
Yeah, I can add 2 points. First, if you are close to 100% accuracy, there is no need to analyze where the errors lies. But if you're not, and your data set is big and you have hundreds of mispredictions, then trying to analyze and understand them and see where the model is good and where is weaker, because what we get whatever accuracy metric we take, whether it's accuracy or F1, whatever we take, it gives us an average. Now, average is as good as average, right? And there are areas that we are better, areas we are worse, and need to see it in the direction of the problem domain we are trying to solve and the business value it gives. And the second thing is when you have a solution and you deploy it to production, I think that the best thing that you can assume that it is as good as what you knew at the moment you deployed it. From this time on, things can happen. Some miracle can happen and the performance will improve, but some things can happen and performance will reduce. This can be since the data nature is drifting or something else that need another analysis and understand how to mitigate and trying to provide these monitors to identify these drifts, and when things are at the border of what you expect it to be, and when they're drifting is also crucial.
Yeah, I like that. And if I may jump in, we also do we run many models. You know, there's one model which is actually running, and then the other models we are in sort of shadow mode. So that there is one model which we think is the best one, and there are other models which are experimental or rubbish, or we think they may be better in the future. And the advantage of that is that normally it's very quick to look up values in the models, but then afterwards when you download the data, you can get 10 times as much live data because you had 10 times as many models, even though only one was actually the one that was used. And so you can do that to speed up research, and you can also do an automatic selection so that if things change on the field, it says, okay, this other module is actually better, then you can switch to that model, so you don't have to bring it home and hardwired to send it out again. Yeah, cool. Yeah, it is. but that's the data you lack all the time is running live, so when you get the opportunity, you try to use it as much as possible. We have a question coming in. Oh, it's from Samit.
Oh, there was, I heard a keynote lately, and I don't know who was, I would remember who was the speaker, but he said that whenever there are researchers that show that whenever there is such a question at the topic of a paper or a talk, the answer is no.
Okay, so it's default no. Can I must see be the well, I think ML can be a performance booster of the next generation. I don't think DS is I think there's too little data in general for that. So ML can be a performance booster for the next generation verification, but not the only driver. As Raviv says a lot of times, is that that whole knowledge framework, you still need all that. You can get to the goal faster, but in the end, you still have to do the validation of the results to make sure that you're not. It's a hybrid model, which is the future.
Guys, we have 1 minute to the end. I let you, Darren, to give you answer to the question, and we close the section. Yeah.
So ML is a supporting tool. It will enable others to apply it and probably enable other unknown ways of doing things or doing things better. But in itself, it's not the ultimate next level verification tool.
All right.
Okay. All right. So thank you, everyone. We're just at the top of the hour. Thank you, and enjoy the rest of the day with DVCon Europe. Thanks.
Okay,
everyone.
thank you.
Bye.
Thanks, Brown. Bye-bye.
Bye-bye.